taking a little bit to load. Alright. Okay. We should be all sorted. So, hello and welcome to the Theory of Statistics workshop. So, this seminar, it's our part 2 of our seminar that we ran yesterday. That would be part 1 covering chapters 1 through to 5, finishing at about, if I remember correctly, transformations. And now we're going to move on to part 2. So I am Otto Ois, and I'll be presenting the convergence of random variables. And then after that, we'll be followed by my colleague, and they will be presenting the rest of the seminar. All right, as per usual, if you have any questions, please feel free to put them into the chat, the comments, and we'll try and answer them promptly, or if you're here in person, I can try and answer you on the spot. All right, so let's get into this. So we're going to talk about the convergence of random variables. So primarily this is looking at central limit theorem, CLT, our big friend, favorite kind of thing. Makes everything a lot easier when we talk about asymptotically distributing a certain function. So asymptotically simply means n going to infinity. Okay? All right. So let's have our motivating question right now. Our motivation right now is, okay, consider the following density function for the distribution of xn. Given that the probability density function of xn at some point x is equal to 2n times x to the 2n minus 1 between where x is between 0 and 1. There we go. All right, so first part of this question is asking us to show that, okay, show that it approaches through some manner d to 1. Now, what does this mean? What is the 1 that we're talking about? It may not be very clear, but we're talking about this kind of distribution of 1. We're immediately at the point 1, it peaks, and we get all of our probability. And similarly, we want to show it probability-wise for part 2. So let's just run through a couple definitions. So first of all, we have a convergence in distribution. That's what this little d stands for, convergence in distribution. Now, we know that if the cumulative distribution function asymptotically approaches a specific function, we know that those two distributions, there's a convergence there, right? From xn to x. This is a very key factor, and so now we go ahead and try to do the same thing here. In this manner, we're treating 1 as a cumulative distribution function, like fx, but it's very special in how it works. So how do we do this? We go ahead and we define, okay, what is the cumulative distribution function of xn? Well, we have the PDF given, so we integrate it from 0 to x, because we recall our basic properties that the cumulative distribution function of x at a point little x is equal to the probability that big X is less than or equal to small x. All right? And so this is a summation, an integral up until x. We would usually say from negative infinity, however, we have that x is bounded. So we're allowed to substitute 0 in there. All right, so we keep on moving forwards. And so we solve this integral, we get x to the 2n, and we have that, okay, for all the points between 0 and 1, our value of this function goes to 0 asymptotically. And therefore, we can go ahead and through a few extra arguments, argue that, okay, well, the limit of this function, the cumulative distribution function, goes to 1. And so, we have the exact same thing we want, okay? This is our argument, and so we show that the distribution approaches that special 1 type cumulative distribution function. It's not set out the best way in terms of our notation, but we understand that this is just the thing we were looking at before. Alright, so on to part 2. What does this P mean? Well, let's go ahead and find that out. The P denotes a convergence in probability. So this is primarily looking towards, okay, what is the probability that the two variables that I'm talking about at some point are different, okay, within a certain bound. So for all epsilon greater than 0, we are defining that if xn approaches x probability-wise, then the limit as n goes to infinity, so the asymptotic convergence, has that the difference between these two variables goes to 0. Alright, so let's apply that. Now, given that this variable here has essentially a PDF of 0 for all x less than 1, right? We can go ahead and say that, okay, well, I simply need to show that xn, as n goes to infinity, has a PDF of 0 for all x less than 1. Fair enough. And so we go ahead and we substitute this in. We know that we're going to 1, right? As we go to, we're talking about fxn of 1, right? So at this point, we're able to substitute it into the equation, and we determine that the union of these two probabilities is actually just the sum of those two independent probabilities, because there's no overlap between them. We're looking at above something and below something. So if we say that, okay, here's 1, and then xn can take some quantity of values left and right, we're looking to find, okay, what is the probability it's in that range or in that range? Okay? So we push forwards, and so we go ahead and say that, okay, well, we understand that it's not going to be anywhere over here. No matter how far we look, how close we look to 1, as long as it's not 1, our probability doesn't exist there. And so we end up with a 0. Okay? And therefore, the limit approaches 0, and so we can just jump back to our formula. Might be a notable formula to put on the formula sheet if it's assessed, but that's just some notation-wise, some notation to be noteful of. That's what I'm trying to say. Okay, so we push forwards. Now we have a new type of convergence. Okay, this is almost sure convergence. This is a rather loose way of saying, okay, if asymptotically the two probabilities are the same, the probability of that being, like, if that's our event, if the probability of that is 1, we say, okay, it should be happening. There's no super rigorous way of saying this. We're just saying that, okay, probability eventually equals this probability. There may be some touchy scenarios, but I digress. We move forwards. We keep on defining more types of convergence. So typically we look at L-squared convergence, and this is the fundamental way that we're going to set this out in our problems. Okay? So as the limit of the expected value between these two different functions to the power, well, the difference of those two functions to the power of p goes to 0, we understand that xn approaches x in a L to the p convergence. Okay? Now, we talk about the strength of certain convergence, implying, okay, this convergence can imply another convergence because it satisfies more conditions. Okay? And so, doing so, we say, okay, we have almost sure convergence, implies the probability convergence, implies a distribution convergence. And this is somewhat intuitive. we have our CDFs, expected value, we have our CDFs being used to give us our probability, and then we are essentially integrating or differentiating that to arrive at our next conclusion. Okay, so we push forwards. Now, here's the big subject that we need to look at. It is one of the big points, at least for one of the 4 questions in the 2901 exam. I'm not super sure about the 2801 one, but we push forwards. So, here's our motivating question for the central limit theorem. We could have looked at maybe the 2024 midterm, but we will use this example because it is rather informative. So, we have 48 variables, uniformly distributed, and we set up the sample mean of these 48 variables, okay? We want to compute the probability that this sample mean is going to be greater than 0.55. So, there should be enough information in this question to actually just provide us the answer outright, just by the computation of our random variables. However, that would be drastically tedious because we have 48 of them. So, what this course proposes that we do is we go ahead and look at a way to normalize and simplify these kinds of distributions. And so this is where central limit theorem comes in. Essentially, any sequence of independent and identically distributed random variables, each with a certain same mean and a certain same variance, which are both finite, we have that, given a sample mean, defined by the averaging of our n variables, this sample mean is distributed normally. And so, we can denote that in a very specific way. This allows us to normalize any summation of variables in a very clean and sorted manner. So we come back to the question. We want to apply this, where we have x bar and we're using the uniform distribution. So, recall, uniform distribution is going to provide us very specific mu and sigma values. Okay, so we know that the expected value of a uniform distribution is halfway along its distribution, so we get a half there, and with help of our formula sheet, we can just grab 1 and 12 here, but rather we would take just the expected value squared, expected value of x squared minus expected value of x all squared, which becomes a little bit more tedious, but that's a few integrals, gives us the answer. So, now we want to apply immediately what we've learned from the CLT, central limit theorem approximation. And so we have x bar here, which we're going to find out how it's distributed. We have our mean here, and then we have sigma squared on n all square rooted, as we like it. Okay. So, we push forwards. I believe... Yeah, okay. Yeah. You want to be a little touchy with whether you're using sigma squared here or just sigma. And so, the way that we avoid this entire mess is we go ahead and we say, okay, well, if sigma squared is 1 on 12, sigma is going to be square root of 1 on 12. Alright. Where was I? Where was I? There we are. Okay, so fundamentally, we can now go ahead and say, okay, since this is normally distributed, I can now rearrange my variables. Okay? I can rearrange it such that, okay, finding the probability that the sample mean is greater than 0.55 implies that subbing it in proves the exact same probability. This provides our z-score, and from a table of values we can determine the probability. Now, this is a very loose case of CLT because it's just immediately transforming it over to z-scores. However, we may encounter some more difficult questions where we should look at the table of values to determine the z-score, working backwards almost. Alright, before we do that, we want to begin defining the laws of large numbers, which really, that's how we know that this thing works. We know that for the weak law of large numbers, the probability distribution, the sample mean is distributed such that it converges in probability to the sample mean. It converges to the true mean. That's what I'm trying to say. There we go. Okay, and we also have a strong law of large numbers. They essentially do the same thing, but we understood that almost sure implies a convergence in probability. But we continue. And so this simply explains that, okay, this approach works because, quite frankly, our sample mean after enough attempts will approach our mean. That's just the statistical definition. All right, so here we have a very interesting piece of information, specifically for the binomial distribution. It's essentially the exact same concept, but little bits and bobs here and there. Since we consider the binomial distribution to be a series of Bernoulli trials, just summed together, we understand that, okay, I know that from before, x bar minus mu over sigma on root n is distributed the same as the normal distribution. Fantastic. But when we start talking about a Bernoulli trial, then we can go ahead and say, okay, for my Bernoulli trial, I have x bar minus p over, well, the standard deviation in a Bernoulli trial is given by p, 1 minus p, and then I divide that by root n. Okay, but then when I talk about that in a binomial distribution, I'm multiplying everything by n essentially, okay? And by multiplying everything by n, well, top and bottom by n, I get the exact same thing, right? So I get x minus np divided by square root of np 1 minus p. Mind you, I should have put a square root here. I forgot to, but that's that. Essentially, this little quick conversion allows us to immediately talk about the binomial distribution rather than building it back up from the Bernoulli distribution. Okay, so, and it explains why it is distributed the exact same. And so, we go forwards. Exact same thing we just covered. And now, we take another peek. The probability that my variable x, my binomial distributed variable x, is less than or equal to small x, so in other words, my cumulative distribution function. This is approximately equal to, mind you, we use approximate because we're almost converting a I forgot the word. We're converting a discrete probability sampling into a continuous probability sampling because we recall binomial is a discrete set, okay? And so we say that this is going to be approximately equal to the probability that my z-score is going to be less than or equal to x minus np plus a half. Now, this half bit is coming from continuity correction, right? So the big thing about continuity correction is that it's particularly notable when our standard deviation, or rather NPQ, of our binomial distribution is pretty small, right? So if this value is small, the differences up here make a very big difference. And I mean, I shouldn't need to explain continuity correction to us, but anyways, we get something like this. If I take the top half, I'm missing out on an extra portion of values depending on how it goes, which way I'm counting, right? So continuity correction simply allows me to say, okay, I'm adding an extra half because it actually counts for a sizable quantity of the probability. All right, now we have our application of this. This is the opposite direction question that I was also talking about earlier. Essentially, 1,000 customers, they choose between two different theaters independently, okay? So that means the probability of choosing a very specific theater is a half, n equals 1,000, and then big N is the number of seats in each theater, right? So having P and N, this gives us our binomial distribution. We want to find a condition in terms of N which will guarantee that the probability of a particular theater turning away a customer because it will be full is less than 1. So in other words, probability that our variable x, so mind you, we're saying that x is distributed binomially, NP, so 1,000, a half. So the probability that x is going to be greater than 1,000. Sorry, greater than n, because n is the number of seats. Okay? We want this to be less than 1%. All right. So let's get on with that. Essentially, what we've just written. Exactly. Word for word. From here, I mean, there's the binomial distribution. We don't want to do that because, wow, that is messy. We have 1,000 choose x, and we're summing from our variable that we want to calculate, which doesn't quite make sense. So we apply our continuous approximation, which is the normal distribution, an application of the central limit theorem. And so we apply our fact here, and we immediately throw it into probability. So mind you, because n is 1,000 and p equals a half, we have that mu is a half of n, which is 500, and we have that the standard deviation is equal to the square root of n p 1 minus p, which is 250. Okay? Fair enough. We want to solve for n in this case. And so we can quite frankly go ahead and say, okay, I have my mean here, I have my random variable here, I can replace this immediately with my normal variable. That's the one. And so now I'm simply finding how many standard deviations accounts for this probability. Okay? And so we push forwards. We want a probability of 1% remaining. And therefore, we go ahead and say, okay, mind you, this is information of the form of the cumulative distribution of our normal distribution. So we say big phi of 0.99 is equal to 2.326, right? Rather, wait, hold up a second. Inverse of 0.99, because this is a quantile function of the normal distribution. And so we have a certain number of standard deviations is placed in accordance with the probability of 0.99. Okay? And what this allows us to do is we say that, okay, well, up here, this equals number of standard deviations from the mean. Okay? And we've just grabbed that from information given, which we would typically get from looking at the table of values, looking at, okay, where can I find 99%, and then working backwards from there. Simply because we do not have a very easy working form of the normal distribution, especially its inverse. Okay, and so we apply it. We say that, okay, I've found the number of standard deviations, and therefore I can calculate n, just by working backwards. And we get our answer. Perfect! Okay, so how do we feel about that question? All right. Okay, so next up we're going to talk about the delta method. The delta method is actually quite an astounding result that we can apply the central limit theorem to. Essentially, given that we have a central limit theorem approximation of a certain distribution with a true mean denoted by theta, the standard deviation by sigma, we have an outstanding result. This is where for any differentiable function in the neighborhood of theta, so that's saying that it is differentiable in the neighborhood. So we have, let's say, here is g. Here's the function g. There we go. If this value right here is theta, in a certain neighborhood surrounding theta, it is differentiable. Okay? It may not necessarily be differentiable at other points, but near theta it is. And that's the only condition we really need. And given that the derivative is not zero. So actually, in this fact, we would not be able to use it. Rather, if theta was instead here, we would be able to use it. So here are just a few condition setting for this very applicable theory. We then say that, okay, taking g of my random variable minus g of my true mean divided by the absolute value of my derivative of my function times the standardized standard deviation, it converges distribution-wise to the normal variable 0 to 1. Now, this is very interesting. We can try and make parallels between this and our several variable calculus mindset and say that, okay, well, I'm taking g of a value, okay? G of some value, g of x. And I'm also talking about g of y, which should be within some distance from g of x, denoted like this, okay? I know that the distance between these two things, if they're close enough, can be approximated by, I'll just say, okay, this thing can be approximated by the derivative of my function at my point x times whatever distance between them. Times whatever distance between x and y. Okay? This is simply because I'm looking at a function, and if I zoom in like really close over here, and I talk about, okay, y that is close to theta has a very specific distance to it in this function setting. Okay? It's almost like a linear approximation. Okay? But we move forwards. It's a very cool theorem and allows us to come up with some pretty funky results. And so let's first just go ahead and show this fact. Essentially, to show that the square root of yn minus p is in its asymptotically, it converges in distribution to the normal variable with a mean of 0 and a standard deviation of, a variance of p times 1 minus p, we simply need to jump back a little bit and say, okay, we know that yn minus p divided by sigma over root n, this is distributed like the normal variable, 0, 1. Fair enough, but that's not what the question's asking. First we can bring the root n up to the top, but we still have sigma here. We note that for a Bernoulli random variable, this is going to be equivalent to p times 1 minus p. Alright, and so from here we can go ahead and say that, okay, well, I'm going to multiply this thing by the square root of p, 1 minus p, of z, because this entire thing can be called z. We take back, from jumping way back, our definition of variance. Our definition of variance is that when we multiply our variable by any factor that's non-zero, the variance is multiplied by its square. And so we can quite quickly go ahead and determine that the mean remains 0 and the variance multiplies by the square of this value right here. And so we get p 1 minus p as required. Fantastic. Mind you, the n going to infinity is brought along and is used in this asymptotic distribution. Okay? Making sure that we account for every piece of information that we've used. And so we go ahead, we apply what we set out to do. We know that sigma is given, and so we multiply and get what we want. Fantastic. Part 2 now. This is looking a little tedious. We have yn times 1 minus yn. Already, this is looking rather dire. However, we just learned delta method, and delta method is super intuitive for this case. Because what if I go ahead and say that g of x is equal to x times 1 minus x? This here is a differentiable function, wherever I look at it. As long as something like p is not equal to a half, so the derivative is 0, I'm perfectly fine. And so, I can go ahead and apply it. So, just jumping back to what we were using, we know that g of y of n times g of p, when noting that this is a Bernoulli distribution, p is our average, our true mean, divided by g dash of p, absolute valued, sigma on root n. This is distributed the exact same as 0, 1. Mind you, this is as n goes to infinity, we're applying central limit theorem. And so, we can pretty much just throw the exact same method at it as before. We understand that g dash of x is going to be equal to 1 minus 2x. And so, things start working out. We know that 1 minus 2x, we're going to take the absolute value of it as well. We push forwards, and we achieve the exact same result in the written working out. Now what's the next step? Well, we've just multiplied it, or rather divided, or whatever, to get our final result. Because all we really need is this root n, yn 1 minus yn, minus p 1 minus p, is distributed like what? We need to multiply by both sides by what is under here. And we apply the exact same fact that we just applied. We apply the exact same rule as before. Okay? So, multiplying both sides by this, we have the square is taken to the variance. It's very, very intuitive in this fact. All right. Thank you very much. This is like the main points of central limit theorem. I wonder what Gary's going to throw at us for 2901, but good luck, you guys. And now I'll be handing over to Kathy. All right.
So, hello, I'm Han. You can also call me Kathy. And now I'm going to go through Chapter 7, Estimators and their properties. So, the definitions of the estimators. Suppose that x1, x2, all the way to xn, they're random variables and they're identically distributed random variables with common PDF fx, where theta belongs to capital theta, which is unknown. So the estimator of theta, which is denoted by theta hat. So how do we actually make a difference between the parameter theta but also the estimator theta is by denoting the theta hat, okay, over here. So the theta hat is any real value functions of x1 to xn. So any real functions of x1 to xn. So when you see here, we have Rn to R. So Rn is that actually you take into the value of all the random variable here, but the output is just a number, so which is Rn to R. The functions of the estimator is to estimate the parameter theta. For it to be effective at doing so, it will need to have certain properties. So let's look at the properties of the estimator. So number one, the estimator theta is a random variables. So this is actually very important because all the property we have gone through for random variable is also applicable for our estimator theta. And also, so in this scenario, we can have our PDF, we can have our CDF, we can apply our central limit theorem, and all of these properties is applicable for our estimator. All right. And second of all, one of the fundamental properties of estimator is our bias. So let theta hat be an estimator of the parameter theta. The bias of the estimator theta hat is defined as the following. Okay, so we have a definition for unbiased estimator is when the bias is equal to 0, or on the other hand, if you rearrange the equations, you will see the expected value of the theta hat is equal to theta. All right, so here's a typical example about the bias. So suppose x is a discrete random variable with property mass functions p of x. And suppose that the space of x is finite, and say D is basically the sample space of A1 to AN. So suppose that x1 and all the way to xn are samples taken from x such that each sample is independent of each other. And what we want to show is the following p hat is an unbiased estimator of p of aj. So in this scenario, we need to show the bias is equal to 0. And then, hence, we'll find the corresponding variance of p hat. All right, so applying the expectations of the p hat will be our first step. And we'll basically just put all these bunch of complicated expressions into here, the expected value of that. With a bit of simplifications, you can get the following. So what does this mean actually? You see a very strange looking I, A of AJ. So what does that mean? So this is actually our indicator functions. So for our indicator functions, I of AJ, and that is equal to, we can have two scenarios. One, if our xi is equal to our aj, or it can be 0 if our xi is not equal to our aj. So basically what we're saying here is it will assigning 1 if the events happened. Otherwise, if the event does not happen, we'll just simply assign it to 0. So here, it's not difficult to find. It's actually a Bernoulli distribution. So it actually can be defined as Bernoulli, and the probability will be P of AJ. So the probability of getting 1 is actually here, the probability of the AJ. So thus, we can have our expected value equal to this one, right? And again, previously, remember, we just put that bunch of equations into our expected value. With simplifications, we can get the following. And then because expected value of the indicator function here, if it's equal to 1, then it's xi equal to aj. So we have the probability as the following. And luckily, the probability of xi equal to aj would just be p of aj. And if you expand this out, because it's a summation, so that would be n times p of aj. And you cancel out with the 1 over n at the front, and in the end, we'll have p of aj. So that is the expected value of our p hat. And if you minus with the p hat, because that's the definition for bias, the expected value of p hat minus p itself, you can see it's equal to 0, which means p of hat is an unbiased estimator. Alright, so after we find the bias of p hat, let's get into the variance of p hat. So it is a Bernoulli distribution. The variance is defined as the following if you check the formula sheet. So again, the variance for that bunch of things, you just put it down. And here's the thing that you need to pay attention to, is if we want to pull out a constant of a variance, then if you put it out, then it should be squared. So inside of the variance, it is 1 over n. If you put that out, it should be 1 over n squared. And then the remaining is the variance of the indicator function si here. And also, you just apply the formula. You will get the p of aj times p minus p, 1 minus p of aj. And finally, this one is also n times of that. If you cancel out with one of the 1 over n squared, you will finally remain 1 as the denominator. Alright, so this is the end for these questions. Let's look at some of the more properties of the estimator. So right now, we have gone through the theta hat is a random variable. So it all the properties of random variable applies to our theta hat. Then we have gone through the bias for our estimator. Then now we are going to go through the variance and the standard error of our estimator. So since an estimator is a random variable, it also has variance. So the standard error would just be the square root of our variance, which is very similar to our normal random variable, right? And so there's one thing we need to pay attention to this slide is, you see this one and this one, they looks a bit different. So for the second one, you also have a little head on to the SE, the standard error. So this is the estimated standard error. So we should pay attention to the symbol out here. Alright, and for our estimator, we introduce a very special property called the mean square error. So why do we actually need the mean square error? So for example, we have our estimator A and estimator B. And for our estimator A, it has a relatively high bias compared to estimator B. But for the estimator A, the variance for estimator A is actually smaller. So in this case, is the estimator A better or B better? We don't know. So this is the case we actually need to apply the mean square error. So the mean square error is defined as the following. So it's the expected value of the difference between theta hat and theta and then squared. And if you do a bit of expansions, we'll find out that the MSE is equal to the bias squared plus the variance. So when you're comparing the two estimators, MSE is a useful matrix that combines the bias and variance. So if the MSE is minimized, we are effectively minimizing the shared contribution of the bias and variance. So we take the bias and variance, both of them, into considerations. So some of you may wonder, how can we get why the MSE is equal to the bias square plus the variance? So here is a quick proving. Originally, we've defined our MSE theta hat is equal to the expected value of theta hat, the difference between theta hat and then square, right? And for inside of the bracket, you have theta hat minus theta squared. And here, you just plus the expected value of theta hat and then minus that. Okay, so if you put in the expected value, it would be just like that. And you put inside of the expected value into it for every term, you get the following. And here as well. So luckily, if you by inspirations, if you look at it, the first term out here is our definitions of a variance theta hat. And if you look at the last term of it, which is the expected value of the difference between the expected value of theta hat minus theta, what's that? It's just our bias, right? And then you see a square here, because inside of here is all a constant, and expected value of a constant is just a constant. So that will be exactly equal to our bias of the theta hat and then squared. So for the second term here, which is our use of blue color, for second term here, if you do the expansion out here, just a little bit of work, you can see that all of the terms here will cancel each other out. So finally, you'll get our MSE equal to variance plus bias squared. Alright, so it's an example time. So we want to show the both estimators on the bias. So again, we want to show the bias equal to 0. So we have two estimator. One is called the theta hat, and one is theta tilde. So let's look at both of them. So number one, our theta hat is defined as the following. So again, for a lot of questions, the first step is always to find the CDF, because then we can represent in a probability form. So what is our theta hat? So what is our CDF? So we suppose U equals to the maximum value of our random variable x1 to xn. And again, if we represent a probability, that will be probability of capital U smaller than U. And because of the maximum of our random variable is smaller than U, so every element of our random variable is also smaller than U. So in this case, the probability of the maximum value smaller than U can break down into the product of each of the random variables smaller than U. So break down into individual probability and then times them all together. Because it is, if you look at the question, it is a normal distribution, uniform distribution with 0 to theta. So then the probability of every item for just one random variable would just be U over theta. Because you can just simply do the integration, right? So for example, you would say 0 to x 1 over theta dt. That would just be x over theta, right? And right now we just represent x with our u. That's it. And because of our CDF over here, you can see that's just one of the random variable, but it has n of them. So times all together, that will be u over theta to the power of n. And don't forget, that's our CDF. So if we want to find the PDF, we just simply take the derivative of it, right? So what we get is over here. And finally, because we want to find the bias is equal to 0, so we have to apply the expected value of it. So expected value of the theta hat, we put out the constant at the front because it doesn't matter, right? We just can pull out the constant at the front. And inside of the integral here, it's u times our f of u. So f of u is defined as here. And you can see it's u to the power of n minus 1. Because of the expected value here, we have to times u inside of the integrand. So finally, you'll have u to the power of n. So this is the actually reason why here it's u to the power of n. And after you do a bit of simplification, finally you can get theta. So if expected value of the theta hat is actually equal to theta, that just proves our theta hat is unbiased estimator, right? Because bias is equal to theta hat, expected value of theta hat minus theta. So after we have proved it's an unbiased estimator for our theta hat, let's have a look for our theta tilde. So again, we applied expected value of theta tilde. So expected value of theta tilde, which is 2x bar, right? And then because the expected value of our constants would just be itself, we can break it down like that. Okay, and that we substitute x bar into our equation. What's that? Be x1 plus x2 all the way to xn over n. If you want to pull out our n here, we will have 2 over n and expected value of all of these random variable, add them up, right? Okay. So expected value of just x1 will be, for these things, we can break down, represent as n times of the expected value of x, right? So at the end, those two n will actually cancel each other out. So we have 2 over n, okay, I'll write it down again, n times the expected value of x, what's that? Would be our theta over 2. Okay, and then finally, if we cancel these out, surprisingly, just give us theta. So that is actually the expected value of our theta tilde, which is theta. And again, this implies our bias for our theta tilde is a bias estimator. So as you can see in our scenario, both of the estimator are actually unbiased estimator because the bias is equal to 0. So which one is actually better? So which estimator will actually estimate our data more optimal? So this is the time we have to use MSE. So again, just recall the definition for MSE. So our MSE equal to the bias squared plus variance. And because in this case, both of them, the bias for them are 0, so we simply just ignore the bias. And that equals to our variance. Okay, so for the second theta tilde, the variance is actually a bit simpler to calculate. So we'll look at that. Look this one first. So our variance for our theta tilde will be 4 times of the variance of x bar. Why is that? Because again, variance of 2x bar, right? Because this variance, if we want to pull out a constant, it have to be squared. So that's 4 times the variance of the x bar. And also, if you look at the formula sheet, it's easy to find that our variance is equal to, I think on the formula sheet is 1/12 b minus a and then squared, because b is equal to theta and a is equal to 0. Finally, we'll have a variance equal to 1/12 theta squared. And also, if you pull that out, because as usual, we have 4 times the variance of x1 plus all the way to xn over n, right? If you pull the 1/n out, that would be 1/n squared, and then times, okay, our 1/12 times theta squared. But don't forget, we have n times, so we times n, and that will cancel 1/n out, which only left off with 1n for the denominator. And finally, we will have 1/3n times theta squared. Alright, so let's get back to look at the variance for our theta hat. Again, because we have our probability density functions over here, and the variance of that will be the expected value of u squared minus expected value u and then squared. So if you apply the formula and times the u inside of here, you get the following. So I'm not going to do the calculation here, but finally what you will get is over this. It's this. Okay, so if you compare this one to the previous case for theta tilde, that would be 1/3n times theta squared. You will see inside it for this variance, for our theta hat, the denominator is actually squared because n times n squared. But then for theta tilde, the denominator is simply just n. So this means the variance for u goes to 0 more quickly. So in this case, our theta hat will goes to 0 more quickly. That means it is a better estimator. Okay, so this one is a better estimator, exactly. We have more of the properties of the estimator. Number 1, consistency. So again, this definition is very similar to the convergence. An estimator of theta hat of a parameter theta is said to be consistent for every epsilon greater than 0. So if the difference between theta hat, our estimator, to our true value of theta is greater than a number that is positive, the probability of that has to be equal to 0, right? Because if it has to be consistent, then our estimator has to be very, very close to our true value of theta. Then probability of the difference between them is greater than a positive number. This isn't impossible. So this is basically the definition for consistent. And also, we have asymptotically normal as usual, and it's defined as the following. Alright, that's all of it for our chapter 7. And we will now go to chapter 8, our estimation and inference. So after we have talked about the estimator, now we actually need the method for estimation. So number 1, we have the maximum likelihood estimation. So let x1 all the way to xn be observations of random variable x with the same PDF here. So our likelihood functions will actually be the product of our PDF. And our log likelihood functions, we just simply take the natural log of our likelihood functions. That's it. As simple as that. Okay. Yeah, so for these slides, nothing important in these slides. All we have to remember is this. Our likelihood functions, capital L, and our log likelihood functions, lowercase l. Okay. So we will quickly use an example to demonstrate how can we use a maximum likelihood function to get our theta hat. For example, here, we want to show our PDF is defined as the following, and we want to show that the maximum likelihood estimator of alpha is the following equation. So how can we do that? Number one, we take our likelihood functions which is the product of our PDF, right? So this is our PDF and a product of them. And so in this case, we replace x with xi, because there are a bunch of random variables out here. And then if you do a bit of simplifications, you will get the following. So that's our likelihood functions, number one. Number two, we need our log likelihood functions, because in a lot of cases, it's more useful for us to have log likelihood functions. It will simplify our calculations. So log likelihood functions will be the natural log of our capital L. If you do apply the properties of natural log, you can easily get the following. And then, since then, we will not look at the likelihood functions again. We'll only focus on the log likelihood function. We take the first derivative of the log likelihood functions L, and we'll get the following. And also, we take the second derivative of L. We'll see it is negative n over alpha squared. And for this expression, it's actually smaller than 0, which means if you look at the functions, the second derivative is smaller than 0. That means the functions itself is concave down. So if functions concave down, you can find the maximum, right? So how do we find the maximum? We equate the first derivative to 0. That's the time we can find the maximum, right? So that if we equate the first derivative to 0, we'll have the following. And finally, it's not difficult to find our alpha. To be more, it should be alpha hat equal to n minus the sum of the natural log of xi. All right. So again, just do a quick review for our maximum likelihood functions. So number one, we get the likelihood functions, and then the log likelihood functions. And then second step, we look at the first derivative and second derivative of our log likelihood functions. And if the second derivative is negative, which means it's concave down, then we have the maximum. And how do we find the maximum? We equate the first derivative of L equal to 0, and then we can find our maximum likelihood estimator. So basically, 3 steps. And we also have some properties are MLE. So number one is consistency. So theta hat is consistent. So in this case, we call theta hat is consistent with theta. And also equivalence. So let theta hat be an MLE of a parameter theta. If g of theta is continuous and differentiable functions of theta, then MLE of g of theta is g of theta hat. Okay, like that. And then number 3, asymptotic normality. Okay, so this is actually just what we have talked. It's very similar. We just replace, now it's no longer x bar or something, it's theta hat. More general case. Now we're going to look at the Fisher information. So you don't necessarily have to look at a bunch of the information out here, but what I want everyone to remember is that we have our Fisher information I of n, for example, theta, is equal to the negative of expected value of the second derivative of our log likelihood functions. That's it. This is the most important thing. Alright, so our variance will be, we have a new definition to define our variance. So variance of theta hat will be 1 over our official information, and the standard error will be the square root of our variance. Okay, that's it. Okay, so a quick example. Suppose x1 to xn, where our PDF is defined as the following, and find the estimated standard error of theta hat, and the approximate distribution of theta hat is known as the following. So we know our standard error is square root of variance, and our variance is equal to 1 over official information. So we can have the following. And so thus, if we apply the asymptotic normality, we have theta hat minus theta over theta divide square root of n is asymptotic. We have the normal distribution that basically it's normally distributed. Those of a bunch of data is normally distributed. So I just want to elaborate the information or the definitions and some of the property here. Again, a very important thing in our chapter 8 is our confidence interval. So let's have a look. So sometimes, usually for our estimator, we say theta, we can say theta equals to 2.5. So that is just a data, just a number, right? But it's more useful or more fantastic if we have a range of data, if we give our estimator a range. For example, it's 2 to 3. It's more better to give us like that because it's an estimator. We're not certain it's exactly equal to 2.5, right? It's better for us to give a range. So that is the time why we need the confidence interval. Alright, so we'll quickly go through a definition here. Okay, let our x1, the random variable, be a sample on a xi, and they have a common PDF. And so alpha is between 0 to 1, and we have our lower bound, which is some functions of a random variable, and the upper bound, which also is some functions of a random variable. And then we said our interval, lower bound and upper bound, is a 1 minus alpha 100% confidence interval for theta if here. So one thing we need to pay attention to is our theta is actually fixed. Okay, so this one is actually fixed. But our lower bound and upper bound is not fixed. That's it. Okay, so the most important thing we need to remember for confidence interval will be the formula out here. Okay, so theta hat plus or minus the z value of 1 minus alpha over 2. So for example, if we want to construct a 95% of confidence interval, so our z value should be 1 minus 0.05 over 2, which will be z value of 0.975, right? We should look at that value. And then times the standard error of theta hat. Okay, so that's how we define the confidence interval. Alright, so you may wonder why we have an equation like that. So why do we have an equation like that? So let's have a look. So how do we define the consistency as asymptotically normal? Is that we have z equal to theta hat minus theta over the standard error of theta hat, right? And that one is normally distributed. Okay, normally distributed 1, 0, 1. So we have the probability here, like this one. 1 minus alpha, which is our probability. That's approximately equal to the probability of the negative z 1 minus alpha over 2 to z values between those two. Alright, so our z is actually can represent in this way because of the consistent and asymptotic normality. So our probability will actually be, we'll just substitute inside, right? Keep the same. And we substitute z equal to theta hat minus theta over standard error of theta hat. That value of 1 minus alpha over 2, like that. So if you rearrange here, you times to the both side, right? And then if you rearrange a bit, you're surprisingly fine. That's exactly equal to this one. Solved. So here for those two couple of slides, it's actually for x bar here, it's just a special case of our theta hat. So we can actually have more general case for that. Yeah, exactly what we're talking about here. So quickly we'll go through a confidence interval example, and then we'll go to chapter 9. So confidence interval here, 5 water samples are taken from the small dam, and the average of 5 values is used as an estimate over the concentrations in our dam. So sample means was here. Okay, with a sample standard deviation 0.006. And we want to construct the 95 confidence interval for our concentration. How do we do that? Again, we have our mean and sample deviation, our sample size, 3 of them, and want to construct a 95 confidence interval for the true value of mu, which is given as the following. So we just simply apply the formula here. So what is our formula again? We have theta hat plus or minus the z value of alpha over 2 times the standard error of theta hat. And our theta hat will be our x bar. Z value of 1 minus alpha over 2 remain the same, and our standard error is s over square root of n. So we substitute the value inside x bar over z value. Z value of 0.975 will be 1.96, and times the standard deviation over the square root of sample size. Fantastic. So finally, our range and value of confidence interval is represented following. Alright, so that's all of the chapter 8, and then we'll go through chapter 9, hypothesis testing. So first of all, we have our null hypothesis, usually defined as H0. So and then we also have another hypothesis called alternative hypothesis, H1. So H1 is a more general hypothesis about the parameter of interest to us. And if we reject our H0, we will have our H1. So our H1 could be double-sided, two-sided, or one-sided. Both of them. This is a double-sided, and for those two, it's a two-sided. For this is a double-sided. For those two, it's a one-sided only. So in this hypothesis, we'll use our data to test H0 by measuring how much evidence our data offer against H0 in favor of H1. So how do we conduct the hypothesis test? We have 3 steps. Number 1, we define and state our null hypothesis H0 or our alternative hypothesis H1. Step 2, we'll use the test statistics to measure how far our observed values differ from what is expected under the null hypothesis. And then we'll calculate the p-value. After we get in the p-value, we will compare that to a p-value table to see if it's greater than 0.05 or smaller than 0.05. Finally, based on our p-value, we will then reject or accept our null hypothesis. So 3 steps. All right, so let's look at a typical example for it. So we have a Mythbusters were testing whether or not the toast lands butter side down or more often than butter side up. So in 24 trials, so n equal to 24, they found that 14 slices of bread landed butter side down. Is it an evidence that toast lands butter side down more often than butter side up? Okay, let's see. Step 1, we define our H0, which is, okay, so again, P is equal to the probability of the toast lands butter side down. So our H0 is, they have equal probability, so a half. And H1 is that, oh, P greater than a half, which means toast lands butter side down more often. Okay, that's our step 1. Step 2, we apply our test statistics. So in this scenario of test statistics, we could look at the asymptotic normality, which is the p hat minus p, or the central limit theorem, both of them, yeah. And then over the standard error, and that will be our normal distribution, normally distributed. And then under our H0, so this one is actually our Z observed value. For our Z observed value, we will put our H0 substitute H0 into our equations, which is 0.5 for our P. So for P here, we substitute 0.5, all of them, and that is also normally distributed for those sample data. And then inside of step 2, we should also look at p-value. So what is our p-value? P-value. Okay, so we have the probability of p hat greater than our p hat, which is defined as 14/24. And the probability of greater than that, if we so that would be the probability of our p hat Z observed, our probability Z greater than or smaller than or equal to the negative value of our Z observed. Okay, and if you put them inside, you will have the following, because it's a negative value. If it turns out to positive, it will be this one. And finally, you have the Z greater than 0.82. If you check the formula page, you can see it's 0.2071 in this case. Yeah. So for this one, if it's a double-sided, we'll be look at the here or here, right? But if it's single-sided, you only look at this part. Alright, so our p-value, we have got our p-value equal to 0.2 something. So we compare to the p-value table to see if it's greater than 0.05 or smaller than 0.05. And you see, if it's greater than 0.05, there's no need for us to reject H0. We'll accept the H0. But if our p-value is smaller than 0.05, then we will reject P0. So this is a normal samples. So in the situation where we have a bunch of random variable over here, we can use the fact that this one, it's basically the same. We just represent our theta hat equal to x bar. That's it, basically the same. So here's an example for normal samples. We will have Okay, so it's before the installations of a new machinery. The daily yield fertilizer produced a chemical plant, which is, the mean is 880. And now during the first day, n equal to 50, first 50 days of operation of new machinery, the sample mean was x bar equal to 888 with a standard deviation 21. So is there any evidence that the new machine is more efficient? Let's see. Number one, we define or determine our H0 and H1. So H0 says mu equal to 880, and H1 says mu is greater than 880. So H0 is exactly similar to before, like which means our new machine is not efficient, is not more efficient than the original machine. And then H1 says, oh, mu is greater than 880, which means our new machine is more efficient than our original machine, right? So step 2, we use our test statistic. We apply the formula here. So this will be a t distribution actually, because we have the sample standard deviation, which is t n minus 1. But similarly, n here is equal to, what is it, 50. So when we substitute inside, we get the t observed. Then our t here will be approximately equal to T49. And if you check, so it's T49 over here. And if this is our T observed. So what we have, X bar is 888 minus originally we have 880. S is our sample standard deviation, 21, over the square root of 50. Alright, so that one will equal to 2.69. If you checked in our studio, you will see, oh, we get something like that. Our probability was something like that. And then compared to the p-value table, it's very, very small, right? So in this case, that indicates we should reject our T0 and accept our H1. Reject our H0 and accept our H1. So we have a word test and also a likelihood ratio test, though for our test statistic. I will quickly go through it and finally wrap up with one of the example. So what is our word test? Step 1, we define our H0 and H1. Step 2, we have our test statistic. Theta hat minus theta null over the standard error of theta hat. Okay, that's normally distributed. And then we substitute our theta null to get W observed. As usual, we should have our W, which is our test statistic, and then we substitute our value inside, we get our observed value. And then we have the p-value, which is the things that I've just talked about. And then that will be 2 times the p-norm functions in our RStudio. Finally, we compare our p-value to the p-value table. We see whether we should reject our H0 or not. And also we have the likelihood ratio test. So before we actually get to know what is the likelihood ratio test, we should pay attention to, we should first have a look at the chi-square distribution. So the chi-square distribution is a distribution of the sum of the squares of k independent standard normal random variables. So the probability of density functions of chi distribution is defined as the following. And the mean and variance will be k and 2k. Alright. The reason why we should introduce this, because if we calculate the p-value, then we have to sort of use these distributions in our studio to help us get the data. Okay, so for likelihood ratio test, first have the hypothesis, H0 and H1. And then we have the test statistic, which will be 2 times the natural log of our, what's this, maximum likelihood functions of theta hat over the maximum likelihood functions of theta naught. And that could be also written as the log likelihood functions, right? Because you apply the natural log inside of here, you get the log likelihood functions. All right. So yeah, pay attention to this formula, lambda equal to 2 times the natural log of what is inside here. So I will quickly use an example to demonstrate the 2 tests. One is Wald test and one is likelihood ratio test. Okay, so number 1, we'll first look at the questions first. All right, so we have a random sample, x1, x2, all the way to xn, x 100, okay, n defined as 100, with our common density functions given by the following. And we want to use different test statistic method to test the following hypothesis, theta equal to 6 versus theta does not equal to 6. So here is some information that give you. So the sigma of xi squared is equal to 14.081, yeah. And our theta hat, which obtained by maximum likelihood functions, is equal to n over the sum of xi squared. Okay, number 1, we use our Wald test. Okay. Step 1. We define our H0 to be theta equal to 6 and our H1 equal to theta does not equal to 6. Number 1 solved. Step 2, we use our test statistic, which in this case is the Wald test, right? Wald. Okay, so W equal to, what is it? Theta hat minus theta null over the standard error of theta hat. That is normally distributed. And so after we have this, we will get our W observed value. Substitute the value inside. So our theta hat by maximum likelihood functions, defined as in the previous slide here, we'll have substitute them inside 100 over xi squared. Take away our, what is our theta null? Theta null 6, and that will be also sigma, which is our theta hat, over square root our sample size 100. That is normally distributed as well. We'll just simply substitute our values inside to get W observed. And also inside of our step 2, we should also get the p-value, which is the 2 times the probability of z minus z smaller than the negative value of our observed. right? Okay. Because it's double-sided, because we have to times 2. And then if you simplify that, offset value will be 1.55, because this value is given, right? This value is given, it's 14.081, right? If you substitute all the values here, you can get a 1.55. Yeah, okay. And by looking at the P norm in RStudio, you'll finally get our P value is equal to 0.12. And if you compare this into our p-value table, you can see this p-value is greater than 0.05, which means there's little evidence against H null, so we should accept H null. Okay, so accept H null. H null, yes. Okay, so this is our wall test. And also, I want to introduce the likelihood ratio test as well. So for the same questions, number one, step 1 will always be the same. So I'm not going to write step 1 as again. I will start at step 2. Step 2. So we have our formula lambda equal to 2 times the natural log of, the likelihood functions of theta hat over the likelihood functions of theta null, or can be represented as 2 and then log likelihood functions of theta hat minus the log likelihood functions of theta null. Alright, so what we have here, we have the log likelihood functions. So you can double check the log likelihood functions, but right now I'm going to write it down. Just write it out. You can double check. Look at the questions again and double check the log likelihood functions, right? Will be our fxi theta here. Because n here is equal to 100, so you substitute inside will be 100 natural log of 2 plus 100 natural log of theta and plus all of these that. Oh my god. Xi minus theta xi squared. Alright, so this is our log likelihood function for theta. And so for our theta hat, because if you look at the equation here, what we want is this one and that one. After we have getting those two, we're done. So how do we get our log likelihood functions of theta hat if we know that our log likelihood function for theta is this one? We just simply substitute our theta with our theta hat, right? So I'm not going to write it out to save time. But also, so this is actually very easy, right? It's theta hat. We just substitute whatever theta here equal to our theta hat. And for our log likelihood functions for theta null, which is 6, this is actually very easy as well. We substitute the theta equal to 6. So finally, you can have our lambda, right? Because you know the log likelihood functions for theta hat and also for theta null. And then you can absolutely definitely find the lambda over here. Alright, so you have lambda and you have the lambda observed. So finally, if we want to calculate the p-value, because that's only the test statistic part, we also want to find the p-value part. P-value, you will see, oh, that is actually equal to the probability of theta equal to 6 and lambda greater than lambda observed. And lambda observed, right now I can tell you, so for this one, observed is equal to 2.689. Oh, so that one is probability of theta greater than 2.689, which is approximately equal to 0.10. So as you can see, if we use the maximum ratio test, the p-value is still greater than 0.05. So compare that to p-value table, we still can say step 3, little evidence against H0. So compared to that, yeah, we accept H0 if we use the wall test. And we'll also accept H0 if we use the likelihood ratio test. So yeah, so basically both of the cases elaborate we should not reject our H0. Instead, we should accept our H0. So basically, yeah, that's the end of the chapter 9, the hypothesis testing. If you have any questions, please post it online, or yeah, you can ask in person as well.
All right. Thank you very much, Kathy. So that brings this seminar to an end, and good luck with everyone and their finals on Friday. We'll see you guys later, and we wish you the very best.